Log on, tune in, find out. Another good idea from Cambridge.
Okay, and also perhaps an apology that I guess maybe there are some people here who are more expert in the things that I do than others, and I hope I don't bore those people who are more expert, because I was going to try and start from things which are hopefully not too advanced. So I guess I should also say another apology, which is so that everything that I do is somehow motivated by the Langlands correspondence, and I'm not really going to say anything about the Langlands correspondence today. So I decided to concentrate, essentially, since this is a sort of algebraic Lie theory semester, to concentrate on things which are more algebraic. And perhaps also I wanted to, at the end, show how some of the things with p-adic groups come down to questions about finite groups of Lie type, which we'll see later. Okay, so I'll start off with some notations, hopefully. Okay, so F is going to be locally compact, non-Archimedean local field, complete with respect to some valuation. So you should think QP, so that's the completion of Q with respect to the p-adic valuation, or some positive characteristic field, so field of Laurent series in one variable, or of course extensions of QP, finite extensions of QP. And then associated to that, we have all the usual notations. So the ring of integers, which is the closed ball of radius 1. So it's the p-adic integers. This has a unique principal, a unique maximal ideal, which is the open ball of radius 1 around 0, which is, has a generator, which is called a uniformizer, which I'll use a variant pi for. So then the quotient there, the residue field, is called the residue field, and so this is some finite field of some positive characteristic P, which is called the residue characteristic. So just something at the beginning about this. So this is the powers of the uniformizer form a fundamental system of neighborhoods of 0 in F, which is somehow separated and exhaustive. So the intersection of all of them is 0, and the union is the whole of F. And similarly for the multiplicative group of F, which we'll think of as GL1, so GL1 has the units of the ring of integers as its unique maximal compact subgroup, and then it has a filtration by the principal of units by powers of the prime ideal again. So F is I should have said, so it's locally compact and totally disconnected, and yeah, so here we have, and again these here form a fundamental system of neighborhoods of the identity in GL1. Okay, so then the sorts of groups that I'm going to look at will be points of some connected reductive group defined over F, and for the purposes of examples, the two groups that I will really talk about will be GLN, so general linear group, and the symplectic group, which I will take to be defined relative to a Witt basis, which gives you this as the matrix of the form, the non-degenerate form. The results that I'll talk about apply to what I would call a classical group, which means include unitary groups and orthogonal groups, but ones where there's no division algebra involved, so no quaternion division algebras. So those are the groups. So one of the things that are going to be important for us are in fact the compact subgroups of these groups. And so I thought I'd start by saying a little bit about what they look like. So the maximal compact subgroups in GLN are all conjugate to, you just take GLN but with coefficients in the ring of integers. Okay, so things in there which are invertible. So maybe I'll chalk in a minute. And so any compact subgroup is in something conjugate to that. So these have it's called the pro-p radical. So it's the maximal pro-p, normal pro-p solvable in some order subgroup. which is called K1, which I'll call K1, and this is the things which, when you reduce them mod P, you get the identity. Okay, and then also a filtration by normal subgroups, where instead of reducing mod P, you reduce by some power of P. And so this is just like the groups that we saw in GL1, so in F cross, and this is somehow the analog. And again, this gives a fundamental system of neighborhoods of the identity. And so one first remark is that if you look at the quotient of the maximal compact by its pro-P radical, what do you get? Well, you just get a GLN over a finite field, over the residue field. So this is where these finite groups are going to come in. So in SP2N, there are rather more compact subgroups. They're not all conjugate to, so what you could think is, well, I just take sort of SP2N and put with coefficients in the ring of integers, and that is a maximal compact subgroup, but there are many more. So in fact, there are n plus 1 up to conjugacy, and so I've drawn them there, so in blocks. The idea is somehow, and I'll draw it again, is that you split into blocks here. In the middle here, we'll get some sort of symplectic group over O, so something like this, but for a smaller size. So this here should be size, I don't know, 2R for some R. And then in the corners, if you think of those together, again, you get another symplectic group, okay, but somehow conjugated. So the entries no longer look like they're in here because it's been conjugated by something like, I don't know, 1 and a uniformizer. So you get something which looks like this. And then you sort of complete the picture in what turns out to be the only way possible. So actually, I hope I've used the same notation. Oh, I've put the R in the wrong place. There's twice n minus R. And so this is how you then complete it. So this is a maximal compact. And of course, this is the special case when R is 0.
So I guess in the lower left there, that should also be PF?
Yes, it should. No, sorry. Yes, it should be PF. Thank you. Yes, that should indeed be PF. Just as well I wrote it again on the board, because I correct my mistakes. Okay, so that's right. Yeah. So these are what the maximal compact subgroups look like, and again, so we can look at their pro-P radical, and what does it look like? Well, it's again somehow things which are the identity mod P, except you only look mod P in this central block and in these outside blocks. So so this should be a P squared now, because the one at the top should have been a P. So that's where you reduce mod P and not in the other blocks. And again, there is a filtration by normal subgroups, which I'm not going to write down. Somehow the idea is that one time you reduce the power, you increase the power of P in these blocks, and then the next time you do it in the other blocks. Okay, and you sort of alternate. That's one filtration you could put. And in this case, the quotient for the maximal compact by its radical is not, in general, just a single symplectic group, but it's a product of two symplectic groups. And again, so you can see them. There's one of them coming here, and the other one coming from these blocks on the outside. Okay, so now let me talk about some representation theory. So the sorts of representations of these groups that I'm going to look at are smooth representations and also complex representations. So first of all, so these are going to be homomorphisms from G into the automorphisms of some complex vector space. And this smoothness condition is a continuity condition. It says that the stabilizer of any vector is open. So if you like, one can also say it as saying that this map is continuous if you put the discrete topology on V. And somehow when this is complex and G is p-adic, somehow the topologies don't mix up anyway, so this is somehow the only sensible thing that you can do is to put the discrete topology. So I should also mention that there are theories for example, mod L representations, which might be interesting to some people here. And some bit, and certainly when L is not P, so it's different from the P of the p-adic field, the theories are broadly similar, but there are some subtleties which mean that certainly so for small L, things can be different. Maybe I'll say a word or two in passing as we go. When L is P, so mod P representations of p-adic groups, of course that's a completely different story, and what I say today has no connection. So then also just a set of equivalence classes of irreducible representations, irreducible smooth. So all representations are going to be smooth always, and complex. So we have the irreducible representations, and what else did I say? Okay, so here are some facts from the representation theory. So the first one is that if you have an irreducible smooth representation, then either it's one-dimensional or else it's countably infinite dimensional. So you can see this, for example, for GLN. So if you had a finite dimensional representation of GLN, you take a basis and you take the stabilizer of the stabilizer of that basis. Okay, so each of the stabilizers of the vectors is open, so you have a finite intersection of open sets, so it's open still. So the kernel contains an open subgroup. Okay, and once the kernel contains an open subgroup, then it actually has to contain all unipotent matrices, because it contains, for example, it contains one of these filtration subgroups, which are no longer here, but things which are one mod some large enough power of P, which has some unipotent matrices, and then by conjugation you get all unipotent matrices. So the kernel has to contain then the subgroup generated by that, which is SLN. So it factors through SLN, so it factors through the determinant. So it must be irreducible, it must have been one-dimensional. Okay, and so one-dimensional representations, so I apologize, so in this theory we call them characters. Okay, so a character somewhere means maybe what you call an abelian, maybe most people here would call it an abelian character. I mean, it's kind of a quasi-character, but most people leave out the word quasi. So if they're not one-dimensional, then they're countably infinite dimensional. Okay, so one word which I'll want to use later is for a special sort of character, which is called unramified characters. Okay, so the unramified characters are characters which are trivial on every compact open subgroup of G. So all the groups which are conjugate to one of these, for example, for symplectic groups. So for GLN, for example, the unramified characters are all given by taking, of course, the determinant first, because it has to factor through SLN, and then the absolute value to some power, some complex power S. And that gives you all the unramified characters. And in general, they form a torus, a complex torus. Okay, so other things. So the reason why compact open subgroups are important is because one of the tools that's been very useful in studying the smooth representations has been restriction to compact open subgroups. And I think this dates back to Mautner, I think in the 50s, who was the first person to look at this. And it's been a very useful technique. And so in a sense, the reason why it's useful is the following result, which says that if you have an irreducible representation and you restrict it to some, have I written what K is? I don't think I have. So K is some compact open subgroup, and you restrict to that compact open subgroup, then it decomposes as a direct sum of irreducible representations, each with finite multiplicity. And in fact, it's even more than just with finite multiplicity. It's even somehow bounded. It's a uniform bound somehow. Also, so since the representation is smooth, right. So then if you take one of the irreducible summands, this is a smooth and finite dimensional representation of the compact group now. And so it factors through some finite quotient. So it factors through some quotient by these filtration subgroups that we had. So it's, again, we're really looking at representations of finite groups. Again, so you can restrict to a compact group. Finally, so Shor's lemma still works, which is nice, but of course Maschke's theorem won't, and in a sense if it did, then it would mean the theory wouldn't be very interesting maybe. So of course it does when you restrict to compact subgroups, it does, but not for the whole group itself. Okay, so those are some basic facts. Okay, so this I'll go through quite quickly since everybody know this. So I want to talk about ways of constructing representations, and the kind of the first method is parabolic induction, which I think is also called Harish-Chandra induction. So you take some parabolic subgroup of G with a unipotent radical n and Levy subgroup M. So for GLN, or indeed for SB2n, certainly in the way that I've chosen the basis, P is just conjugate to block upper triangular with some block sizes. N will be the subgroup where you get the identity on the diagonal blocks, and M is just the diagonal blocks. And so what you see then, so for GLN, the Levy subgroup is isomorphic to a product of copies of smaller GLNs. And for the symplectic group, well, you get a product of smaller, you get one symplectic group and then a bunch of GLNs whose sizes add up to the right thing. The point is just that if you want some sort of inductive definition of, or characterization of all the representations, this is very useful, because if you've done all smaller GLNs, you can hope to do larger ones. And likewise, for symplectic groups, once you've done smaller symplectic groups in the general linear group, you can hope to do the larger ones. So, so of course, what you can do then is, if you have an irreducible, let's say, representation of a Levy subgroup, you can induce it up to the full group. So first of all, you inflate it to the parabolic, and then you induce. So what I've done now is I've written down the definition of induction just to sort of make one small point. So this is the model of induction that tends to get used is in terms of space of functions. So it's the space of functions which, so essentially transform from G to the space of our representation, which more or less transform on the left under the representation Tor. And so this is actually what's called compact induction, I've just realized. But it's the same here. So, but it's not quite just that they transform on the left under Tor. There's a normalizing factor here, and this is the modulus character. And what this does is it takes into account somehow the effect on the measure of a conjugation by P. So the point is that for the parabolic subgroup, a left Haar measure and a right Haar measure are not the same, and this somehow characterizes the difference. So I think so. At least here's one definition of this modulus function is that. So if so K here is going to be a compact open subgroup of P, and this is the so generalized index of conjugation. So it sees how conjugation, as I say, how it changes the measure, how it affects the measure. Okay, so for the group G, if this had been if P is the whole group G, this is trivial. Yeah, but in general, for parabolics, this is not trivial. And the reason for putting this in, so you get, this is what's called normalized induction, is, so for example, to make sure that unitary representations induce to unitary representations. Okay, because not everything is unitary. Okay, so the second condition here is just to make sure that you end up with a smooth representation. Okay, so a priori, if you look at all the functions which satisfy the first thing, there'll be some of them which, and so G is going to act on the right with the right regular action, in general, some things won't be smooth, so they won't have an open stabilizer. So this is just making sure that you just take the smooth vectors, and the last condition is actually empty here, because G mod P is compact when P is a parabolic subgroup. But I put it in here because later on I'm going to want to induce from different sorts of groups, and I want to have this sort of induction. So this condition is sometimes put in and sometimes not. If it's put in, then it's usually called compact induction. But for induction from parabolic subgroups, compact induction and normal induction coincide. So okay, so what you get is a smooth representation of finite length, which depends only on what you started with in particular, it doesn't depend on the parabolic subgroup, and this is another reason for putting in this normalizing factor. Okay. So here are some examples, I hope. So here's an example with GL2. Okay, so in GL2 there are not many Levy subgroups to choose from. So there it is. Well, not many proper Levy subgroups to choose from, I should say. So M is just a diagonal group, the diagonal torus. P is the Borel subgroup. And so then a smooth representation of that is just the tensor product of two characters, chi1, chi2. So these are smooth characters, so this means they have open kernel. Okay. And then what one can check is what happens when we induce. So when we induce, you get something irreducible. And the only time you don't is when chi1 and chi2 differ by just the absolute value function or its inverse. Okay, and then there are kind of two things that can happen. So depending upon whether it's chi1, chi2 inverse is the absolute value or if it's inverse. So either you get a one-dimensional subrepresentation and then an irreducible quotient when you quotient that out, or you get a one-dimensional quotient with an irreducible subrepresentation which isn't one-dimensional. Okay, but in each case there's a unique irreducible subrepresentation and a unique irreducible quotient. And so, of course, one of them is a character and the other one is a generalized Steinberg representation. Okay, so it would always have length 2. So actually, since I mentioned mod L representations earlier, I mean, there's a good point to give an example where it's different for mod L representations. So if let me get this the right way around. If P is -1, so if P is -1 mod L, I think that's the right way around, then you can actually get something of length 3, okay, which has characters at the top and the bottom, and then something irreducible in the middle, and so it's things that. Anyway, so these irreducible representations here they're called principal series representations in general when you have the Borel subgroup. That's what you get. Okay, so then if we have these representations which we get from parabolic induction, so then there are still all the rest, the ones which we don't. So these ones are called cuspidal, and so ones which don't occur as a sub-representation of any parabolically induced representation for a proper Levy sub. And so there's a theorem which I'm not entirely sure if it is Jacquet or not, or maybe I read somewhere that it was Harishchandra as well, but so I'm not quite sure. Anyway, which says that essentially it says that understanding parabolic induction and cuspidal representations is all you need to do. Okay, so because if you have any irreducible representation, then you can embed it as a sub-representation of something which is parabolically induced from a cuspidal. So from a cuspidal of the Levy, and moreover, this Levy and the cuspidal are unique up to conjugacy, and this is the cuspidal support. Okay. Oh right. So before I don't want to go on to that yet. Oh, that one's not working. Okay. So when one looks at these representations by restricting to compact open subgroups, of course, when you restrict to compact open subgroups, you lose some information. In particular, so I had these characters which are called unramified characters, or the ones which are trivial in every compact open subgroup. Of course, you're going to lose those. Yeah, it doesn't restrict to compact open subgroups. Doesn't see those at all. And so, in order to somehow get around this, one needs a slightly weaker notion than just conjugacy, and a slightly sort of weaker notion than cuspidal support, which is what's called inertial support. And so that's what I want to say next. So on these pairs of a Levy subgroup and a cuspidal representation, we can put an equivalence relation, which is given by, so first of all, conjugacy. So you'll add conjugacy. And secondly, by twisting by these unramified characters. So if you have a representation, you can tensor it with some unramified character, and that gives you some other representation. And so we want to say that two are equivalent if you can get from one to the other by a conjugacy and a twist by an unramified character. And then it turns out that one can use this to decompose the category of representations. So here's MT with a G to represent the inertial equivalence class, and BG, which is called the Bernstein spectrum, for the set of all inertial equivalence classes. And then we use each inertial equivalence class to define our subcategory of our category of smooth representations. So it's the subcategory which consists of representations, all of whose irreducible subquotients have their cuspidal support in here. So in other words, they all have cuspidal support on, well, so a conjugate of M and tau up to twisting by some unramified character. Okay, and then the big theorem due to Bernstein is that the category decomposes. It decomposes the category somehow into sort of blocks, as a product of subcategories. So in other words, this means that any smooth representation decomposes as a direct sum of objects in each of these subcategories, and there are no morphisms between the different categories. Okay, so I've actually forgotten what I was going to say next. So then what we need to do, let me just go back, is just understand these subcategories. Okay, and the method well, a method at least that we can use to try to understand these is what's called the theory of types. Okay, so this is due to Bushnell and Kutzko, and so the idea is to try to identify these categories as some module category over a Hecker algebra. Okay, so the problem is just to find the right Hecker algebra, and to do this, what you look for is a certain compact open subgroup and an irreducible representation of that, which are somehow going to be going to identify this category. Okay, so which are somehow typical for it, which I think is why they call them types. To find a pair, K rho, consisting of a compact open subgroup and an irreducible representation of that, which has the following property, so that for irreducible representations of G, they're in this category. In other words, their inertial support is this S, if and only if rho is somehow contained in pi. Another one way of saying that is if you restrict pi to k, you'll find rho there when you decompose it into irreducibles. Okay, and if this does happen, then so we can define this spherical Hecker algebra. So this is one way of defining it is as the endomorphism ring of the induced representation, and there's an equivalence of categories then between the modules over this Hecker algebra and the category that we're interested in. And such a pair is called an S-type, so S being the inertial equivalence class. And I don't think I wrote this down. Let me just check. I think I forgot to put this in. Tell you what the archetype. Yes, no, I won't. So the archetype, the first type, though, before the theory of types, is due to Borel, and it's that you take. It's exactly for principal series representations. So one inertial equivalence class in any group is given by taking the Borel subgroup. Sorry, this shouldn't be Borel subgroup. I guess I want a split group. So by taking a maximal split torus and the trivial representation of this torus. Okay, so this defines an inertial equivalence class. Okay, and so what's the what is the type for this? Well, the type. T A is so this is the Iwahori subgroup, which for GLN at least, this is things which are upper triangular mod P. So this is this in GLN. And so it's this and the trivial representation of the Iwahori. Okay, and then this Hecker algebra is just an Iwaori Hecker algebra, which is described by relations and generators and relations. And so this is what this is due to around in the 70s. Okay, so this is a kind of at one extreme in that these are somehow the most induced representations, so the ones that are furthest from being cuspidal. So one can also ask about types for cuspidal pairs. So this means that the inertial class, so the cuspidal support, is just the representation itself. In fact, so it's just the representation and well, its equivalence class. So I'm just going to talk briefly about types for cuspidal representations. So it turns out that all known cuspidal representations, and conjecturally at least all cuspidal representations, can be constructed by induction, which is odd since they're the ones which don't come from induction, but by induction from different sorts of groups. So by induction from compact mod center groups, open compact mod center subgroups. So in a symplectic group, the center is compact anyway. So compact mod center is the same as compact. So for symplectic groups, it just means by induction from one of these groups in, let's say, GLN, you have to put in the center as well. So they're all, and well, yeah, yes, I guess. So I guess not what's not true. So I should be slightly careful. In GLN, so if you take a maximal compact subgroup, so which is conjugate to GLNO, and then put in the center, that is a maximal compact mod center subgroup. But not all maximal compact mod center subgroups are conjugate to that. There are actually more, which come from non-maximal compacts somehow, but which have a bigger normalizer. Okay. So they all come by inducing from a compact mod center subgroup some irreducible representation. Okay. And in fact, actually, even more than that is true, at least in all. So that bit is certainly conjecturally true for all, I think. Well, I say conjecturally, I think this is a sort of folklore conjecture. I don't know that anybody's written it down. That bit is conjecturally true for all groups, I think. What also turns out to be true, so this is known to be true essentially by construction in various cases. But what turns out is that if you then take your irreducible representation and restrict it to the maximal compact subgroup of your compact mod center subgroup, then it remains irreducible. Okay, and then this pair is in fact an S type. It's a type for, I haven't written down what S is, have I? So S there is the inertial class of pi. So pi, which was this induced representation.
Is this compact induction?
So this is compact induction. So it's the induction that I defined before, because I had the compact in. So actually even there, I could have cheated and actually left out the compact here as well. So it turns out that when you induce from a compact mod center subgroup, even if you use non-compact induction, if it turns out to be irreducible, then whether you've done compact induction or not, you get the same thing. So actually, in the end, it doesn't matter. It's not obvious, but in the end, it doesn't matter whether you use compact induction or not, which is kind of strange. So in fact, in both cases, it didn't matter, but for different reasons. Okay, so then here's a theorem that, in fact, this is all cuspidal representations in various cases. So for GLN and SLN, this is due to Bushnell and Kutzko. So actually, I should add that yeah, so I guess this theorem, in a sense, has a long history. And some of the first results, I think, in terms of constructions of cuspidal representations go back to Howe in the 70s. And then there have been various sort of partial results in between. But the first one, which sort of works for all n and all p, shall we say, so this is Bushnell and Kutzko in their book in 91, and for SLN as well. So level 0 representations, I'll come back and explain what those are in a minute. So for an arbitrary group G, so this is due to Morris and also independently to Boy and Prasad. There are also results for arbitrary group not just level 0 representations, but with conditions on the field. So, for example, conditions of the sort that P has to be big compared to the size of the group, that it's not too ramified as well, and characteristic 0, I think. And so there are some constructions due to U which go back to 99, and then in 2006 Kim proved that at least with these conditions on the field, these extra conditions on the field, this gives all cuspidals. For what I call classical groups, so what I call classical groups at the beginning, symplectic, orthogonal, and unitary groups with P odd, so I did this in 2006, and also for GLN of a division algebra, so these are inner forms of GLNF. So Sécher did many of the constructions, and then together we proved that gave everything. So that's cuspidal types. Okay, so just a little word about how the constructions go, without going into details. So all the constructions end up being broadly similar. Okay, so what you do first is you construct using some sort of arithmetic information, you construct a compact open subgroup of G and a very special representation of this group. And it really is very special, and actually, in a sense, constructing this representation, kappa, is the hardest bit in this. So it has to have nice properties, like it kind of has to be intertwined by as much as possible somehow. Okay, so and then what happens? So this compact open subgroup also has a pro-p radical, just as we're seeing for these. And if you take the quotient, then you get a product of reductive groups. In the same way that here, just this quotient was a product of two symplectic groups. In general, you might get more than two. They might not. So even if I started with G as a symplectic group, the sorts of groups I might get here, I might get unitary groups, I might get orthogonal groups, and orthogonal groups, I mean the full orthogonal group, even not just the special orthogonal group. So this is not connected, and the fields that they're defined over might be some extension of the field that we started with as well. So and we take an irreducible cuspidal representation of this. So cuspidal it's in the same sense, but in the sense of representations of finite groups. And then we inflate it. So we think of this cuspidal representation of this quotient as a representation of J, and tensor these two representations together. And this is what gives us our cuspidal type. Okay, and then so in the what's called the level 0 case, the group J is actually a maximal compact. So it really is something like this in the symplectic group. Okay, so then the quotient here really just would be a product of two symplectic groups. Okay, because this special representation kappa, very special, is the trivial representation, which of course is very special. And so you really just, the data that you're using to construct cuspidal representations really just does come from finite groups, from cuspidal representations of finite groups. So here we have two of them. So this is somehow why this was maybe a slightly easier case, because there were lots of results from representations of finite groups, which could be used. Okay, so what about the non-cuspidal types? So if now, instead of having a cuspidal representation of the whole group G, we have it of some proper Levy subgroup. Well, since we've seen, so Levy subgroups are just the same sorts of groups as the big groups somehow, but smaller, and we have cuspidal types for those. So for example, for classical groups, Levy subgroup is going to be a product of a classical group and a bunch of GLNs, and we know all the cuspidal representations for those. So, and we also have types for them all. Okay, so we can look in, I guess, in the category of smooth representations of the Levy subgroup. We have types. Yeah. So we kind of have two categories now. We have the category of smooth representations of the Levy subgroup and the category of smooth representations of the big group. And So in here we have some class S, some Bernstein, some element in the Bernstein spectrum with some inertial class here. And if we just think of this representation Tor as a cuspidal representation of M, we also have a class here. So this is what we call SM. And so we can cut out then these pieces of the full category of representations and essentially try to relate these two things. So here we have we assume that we have a type here, okay, which as I said that we have cuspidal types now in many cases, and the idea is to try to use that to build a type here in the full category for the big group. Okay, so we suppose we've got a type there which I call Km rho m, and P is going to be some parabolic subgroup with levy M, P minus its opposite, and so I've just said, so the idea is to use this type to build something which will hopefully be a type in the big group. And so the list of properties that we need are the following. So the first two are fairly straightforward. We want to find a compact group in our big group which will have an Iwahori decomposition. So we can decompose it into, let's say, sort of the lower triangular bit, the diagonal bit, and the upper triangular bit, so that the diagonal bit is what we started with. So it's what we started with in the levy. And likewise, the irreducible representation should just be given by what it is, what we had on the levy. So here we just ignore what's in the lower and the upper triangular things, so in the unipotent parts. And the last condition is a little odd. Well, it looks a little odd at first. So it's something about the Hecker algebra of this representation, and it should contain a certain invertible element. Okay, so it's an invertible element which is supported on, first of all, on a unique double coset. So there'll all be on a unique KK double coset, and the coset of some element which contracts one of the unipotent radicals and contracts one of them and expands the other. Yeah, one way around or the other. It doesn't matter which way it is actually. Okay, so this is what's called a strongly positive element, and somehow the idea of having this is that you can use somehow the compact parts of the Hecker algebras for rho m in the levy and for rho in the big group are easy to relate. So things whose support is somehow small is contained. Well, I guess it's contained in the levy maybe. No, and you can use this element then to translate it somehow. You can use the fact that it's invertible to translate everything to get an embedding of Hecker algebras. And so the theorem is that in this situation, so this K and rho that we built with these special properties is a type of the right thing. It's called a cover of what we started with. There's an algebra embedding, in fact, and this is where you need this last property to build this algebra embedding of the Hecker algebras, such that, so this diagram here commutes. So we have the induction here. We have these equivalents of categories when we have a type. So that's this one, and this here is induced by tensoring with it's just tensoring with HG rho over here via this embedding. Okay. So in particular, what's useful about this is that if you know the Hecker algebras and you know the embedding, then at least in principle you can learn about induction here. You can learn, particularly what's interesting is the reducibility points of this induction. Okay, and because in principle you can translate this to a question of this side, which can be answered. So what I wanted to do was give an example, say example, loosely an example, I suppose. So this is an example in SP 2n plus 2, where in the end, so this is in SP 2n plus 2, and I want the levy in SP 2n plus 2, which has a 2 by 2 block in the middle. So it looks something like this, G, H, and here I will have something like G transpose inverse. Well, G, it's actually transposed with respect to the wrong diagonal. And so this will be something in the symplectic group, which is sp2 is SL2. So this is the levy. And so if I have an irreducible representation of this, then, well, so the irreducible representations which have certainly some fixed cuspidal support, some fixed inertial support, sorry, all take the form written here. So I take Tor 0, a cuspidal representation of this piece, okay, and a Tor prime, a cuspidal representation of SL2, okay, and then all the things with that support are given just by twisting by unramified characters. SL2 doesn't have any unramified characters, but or the symplectic group, and for GLN, we saw that they're just given by the determinant, the absolute value to some complex power. Okay, so these are the representations that we want to look at, and the question is, for which values of which complex values of S is this induced representation irreducible, and when is it? Well, actually, I guess most of the time it's irreducible. So I guess the question should be, for which is it reducible rather than irreducible? Okay, so so first of all, there are a few things which one can get relatively easily. The first thing is that if none of these representations is self-dual, so of course there's a question of duality on representations, a smooth dual. If none of them are self-dual, then there are no S like this. Okay, so we might as well assume that Tor 0 itself is self-dual. And so if it is self-dual, then one can actually compute these values from the parameters in certain Hecker algebras over finite fields. So I'll try and explain how this works. Okay, so briefly, here's the idea. So this is some notation. Like here we have here a type for the cuspidal representation here, and on this side we have a cover which I've now put p's in. JP lambda p. This is a cover, so this is now a type for this inertial class here in the big group, and it turns out that yeah. So this one, as I kind of described briefly, these cuspidal types can always be written as a product of some representation here and something which is inflated from a representation of a product of finite groups. So J mod J1, reductive groups over finite fields. And it turns out that this lambda p can also be decomposed in a similar way with the same representation here. I really do mean this. So the point is that Jm mod its pro p radical is isomorphic to Jp mod its pro p radical. So the only change comes in the levy. And so the idea then is to find a slightly bigger compact open subgroup, which, well, in fact, what we want is, so there are some things in here, there are some essentially Weil group elements which are going to do some sort of swapping of things here, but those Weil group elements are not in the group JP. Okay, so they're in some affine Weil group, they're not in JP, but if we can find a slightly bigger group which does contain one of these, then we can learn something. So this is the idea, is to find a slightly larger compact open subgroup, whose, again, we have so we take the J mod its pro p radical, we get a reductive group over a finite field with the property that JP, so the image of JP in that quotient is some proper parabolic subgroup, and the levy is exactly the levy on which this is actually exactly the group on which sigma m is defined. And then it turns out that we have a support-preserving algebra embedding of the Hecker algebra here. So this is now just a finite group over, so a reductive group over a finite field here. This is a cuspidal representation of a levy subgroup of that. and this embeds into our big Hecker algebra. Okay, and so the idea is to try and then use these, and in fact, ideally, the idea is not to have just one bigger group J, but actually two of them, okay, for two different Weil group elements. So here are a few more details for level 0 representations. So for level 0 representations, the group, I've written JM. Yes, that's right. So the group JM here is just GLN O times SL2O, so it's just the maximal compact in here times the maximal compact in here. Okay, and this is level 0, so this bit doesn't have, there's no kappa M, it's the trivial representation. So I can write this as a product of, so sigma 0 and sigma 1, a tensor product of sigma 0 and sigma prime, where sigma 0 is a cuspidal representation of the GLN over the finite field, and sigma prime is a cuspidal representation of SL2 over the finite field. And so one thing that's not completely obvious, but it's not too difficult, is that because our original representation, our representation is self-dual, that means that the sigma 0, the cuspidal representation on here, must also be self-dual, which already restricts things. So it either means that we've actually got n equals 1, and sigma 0 has order at most 2, so it's either trivial or the quadratic character, or actually n has to be even. Okay. So now the group JP, now this one is right, he says. Yeah, this one is right. Okay. So this is the group that in fact you end up with JP. So as I said, so in the levy you see in the top left the GLNO, in the middle the SL2O, and in the bottom right the sort of the translated copy of the GLNO. And this is contained in two different compact open subgroups. So this JP is sort of a sub-maximal compact open subgroup. And so it's contained in, well, this one, well, SP, well, it's 2n plus 2 now, and also in this one where this block size is size 2. Okay, and the quotients, so we've seen, so we have one which is SP 2n plus 2, and the other one a product of two symplectic groups, so the smaller one has size 2. And so here are the two Weil group elements which I was talking about. So the one on the left is something which you can see is going to swap the blocks here. So it's something which we might expect to see in the see supporting something in the Hecker algebra, and that's contained in this one. And the other Weil group element is going to be contained in the compact open subgroup, which looks like this. Okay, so first of all, when n is even, when n is 2m, so n, I remind you, is the size of this block here. This is 2. Okay, so on this side, it's always the same. And the reason why it's always the same is that somehow because the center part and the outside bits are kept separate, you don't get any interaction between what's happening in the GL and what's happening in the SL2 somehow. And so you always get the same, you always get that this Hecker algebra is two-dimensional, and the generator has a generator supported on this element with which satisfies this quadratic relation with this particular power q to the m. If n is bigger than 2, then on the other side, so on the side of this maximal compact, well, in fact, it's always two-dimensional as well, I should say. But you get something with generator with the same quadratic relation, really the same power of q. If n equals 2, well, then it depends. Okay, so it depends on some compatibility condition between sigma 0, which now I remind you, so this is a cuspidal of GL2, and this one is a cuspidal of SL2. Okay, so it's some sort of factoring through some norm or something with condition. And then it depends, and you either get so m is 1 now, here, when n is 2. So you either get the same, or you might get q cubed. So when this condition is satisfied, you get a larger power. So I should also say what happens if n equals 1. So if n equals 1, then on this side, the thing around the outside is just a copy of SL2. And now you're just inducing either the trivial character or the quadratic character of SL2. And so if it's the quadratic character, then you get something irreducible. That's right. So you either get q or 1 as your parameter. So by the parameter, I mean the power of q that's there in the quadratic relation. Okay, and on the other side, so on the side of, well, it's now SP4, you either get q squared or q. So you get q squared precisely when you have the quadratic character in GL2, and for SL2, you get one of these exceptional cuspidals which have smaller dimension, which have half the dimension of the usual cuspidal. And that's exactly the time that you get this. So what does this tell us? So we've found these parameters. How does that help us? Well, it turns out you can just write down a formula. I should say, so this is actually a collaborator of mine, Corinne Blondel, who wrote down this formula. So I don't know that anybody else has written it. Anyway, so if you write VA and VB for the exponents of Q, then this formula gives you the reducibility points of the parabolic induction, okay, in this case. And so now, having said at the beginning, I wouldn't say anything about the Langlands correspondence. This is the only bit I'm going to say. So for the Langlands correspondence, the things that we're interested in is when you get reducibilities with real part of S greater than or equal to 1. Okay, because these should determine the correspondence somehow. So the times that you get reducibilities for greater than or equal to 1, it's telling you something about a sort of base change from an SL to a GL somehow. You can identify from these what the Galois parameter should be in the Langlands correspondence. And so just to write down when that does happen, okay, so first of all, if you take any sigma prime cuspidal representation of SL2 and the trivial character of GL1, you always get reducibilities at plus and minus 1. If you take one of the exceptional cuspidals of the SL2 and the quadratic character, then you get reducibilities here at plus or minus 1 and plus or minus 1 plus pi over log q. And finally, if we don't have an exceptional one, but in GL2, we have the one that I said was somehow compatible, so the one which made a difference. So then you also get reducibility at plus or minus 1. Okay, and it's interesting that this compatibility condition it never applies with these cuspidals. So you can never have a compatibility with those cuspidals. Okay, so maybe just to finish a quick word. So this was for level 0 representations. For non-level 0 representations, you end up looking at similar questions, but instead of looking now in symplectic groups, you end up looking actually in orthogonal groups or in unitary groups. Okay, so this is because I said, so when you have something which isn't level 0, and so you have this rather complicated representation here, the quotient of J mod its pro P radical becomes something, some reductive group over a different field. Okay, so in fact, in this case, it'll be over some quadratic extension. Okay, and so it could be a unitary group, or it could in fact be an orthogonal group as well. So, but one can do it, and so just to say at the moment, so one of the things that I'm trying to work on with Corinne Blondel and Kienia is to try and do this for SP4 rather than SL2, which is kind of a toy example. And just as a little example, if you take in the level 0 representations, one can take here, so now the trivial representation of GL1, and if one takes an SP4 in the middle and we take theta 10, so this famous cuspidal non-generic, well, I would say non-generic, and that's not the word I don't remember the word that you use. This famous cuspidal of SP4, then you get some even more interesting reducibilities. You get reducibilities at plus or minus 2, as well as plus or minus 1 plus pi over log q. So, okay. Well, and I'll stop there. Thank you.
there any partial results for determining when two hospitals are in the same packet or classical groups?
Well, so you mean explicitly? I mean, so there are results of Mogelin, which I think are conditional on the results of Arthur, which say kind of what I said here, which is that you can determine the L packet by the reducibilities of parabolic induction. And so if you have two cuspidals which have the same reducibilities at the same points with the same cuspidals of GLN, then they're in the same packet. So that much yes, but actually explicitly computing the packet, the answer is not yet, no. Yeah.
So you mentioned there are also a number of results for representations in characteristic L, where L is not in the P. For example, what is known there about cuspidal representations? Is there the picture anywhere as complete or at
certainly
least
not as complete? Certainly not as complete. So GLN is done. GLMD is done. Yeah. No. Okay. Okay.
For example, your
SL2 is done, but my results. The answer is no. So the constructions of the cuspidals have a sort of in a sense, the complicated part is a bit which is pro-P, and so there it's exactly the same. It makes no difference, and those bits are the same. But I don't, as far as I know, nobody has tried then to go for, certainly in the generality of classical groups or something like that. Nobody has then sort of tried to go on and do what happens at the top. But that's kind of a project for to look at. I mean, the only am I right? Do you know any? I think SL2 is the only group, apart from GLN. I think SL2 is the only group that has been done
The
properly.
other questions?
So if not, let's thank Sean again.